So let us understand this next very interesting concept. Now here we have an object in front of us, right? And this object right now is at rest and its initial velocity is 0 meters per second. But now I apply force on this object. As soon as I apply force on this object, you see that this object has now moved, right? Now since it has moved, we know its velocity has changed. Now since its velocity has changed, can we say that acceleration has taken place? Because acceleration is nothing but change in velocity. But here the acceleration that is caused due to me. So I can say that this is acceleration due to me. But now we'll change the scenario. Instead of me pushing this object, what we are going to do is we are going to suspend this object by the crane. Now what we'll do is we won't be applying any force. We'll simply leave it from the top. Now again you see it has fallen down. Initially it was at rest, that means its initial velocity was 0, and it has now fallen down, or we can say it started moving. That means again we can see that there was acceleration. But did I apply a force on that object? No, right? That means here the acceleration is caused due to the Earth's gravitational force, and this is what is called as acceleration due to gravity, which is denoted by small letter g. Now we'll obtain or try to obtain the formula for acceleration due to gravity. Now we'll write the definition of acceleration due to gravity. So the gravitational force due to the Earth on an object or a body results in its acceleration, and this is what is called as acceleration due to gravity. We also have a formula for acceleration due to gravity. Let us derive the formula. So to derive the formula for acceleration due to gravity, we need to know two formulae. The first formula is the formula for force of attraction, that is capital F is equal to capital G m1 into m2 upon r square or d square, whatever you may write. So this is the formula. Now what we'll do is we'll make certain changes over here. So here instead of m1, we'll take mass of the Earth, that is capital M, and instead of m2, we'll take mass of the object or a human body, that is small m. And the distance between their centers we know is denoted by small r, but here the distance between their centers will be nothing but the radius of the Earth denoted by capital R. Why? Because the person's height is negligible when he's standing on the surface of the Earth. Now we'll substitute these values in this equation. So capital G remains as it is, m1 becomes capital M, m2 becomes small m, and small r becomes capital R square. So we have capital G, capital M, small m upon capital R square. This becomes equation number 1. Now we need to know another formula, that is nothing but F is equal to mass into acceleration, that is m into a. Now here we know that the acceleration is due to gravity, which is denoted by small letter g. So instead of a, we substitute g, so we get F is equal to mg. Now this is our equation number 2. Now look at equation number 1 and equation number 2. We can see that the left hand side is nothing but the same, that is F. That means the right hand side will also be the same. So here what we obtain is mg is equal to capital G, capital M, small m upon capital R square. Can we cancel something? Yes, we can cancel m and m. So what remains? Small g is equal to capital G, capital M upon capital R square. This becomes the formula for acceleration due to gravity. So here if you see, if you want to remember, in the formula of small g, everything is capital. So remember this, in the formula of small g, everything is capital. Now one thing that we need to understand is that capital G is universal constant of gravitation and small g is acceleration due to gravity. Universal constant of gravitation is called as the universal constant of gravitation simply because its value does not change, but the value of small g can change, and that is what we are understanding right now, the variation in the value of small g. Capital G cannot change, small g can change. This is really sad, right? Because the reasons for the variation in the value of small g are really sad, because S stands for shape, right? So S is shape, A is altitude, and D is depth. So these are the three reasons why there is variation in the value of small g. We'll understand each of them in detail. So first of all, we'll understand shape. So when we understand shape, we know that Earth is actually not spherical. It is geospherical. That means it is actually flattened at the poles and bulging at the equator. Now, since it is bulging at the equator, here what we need to understand is we have the formula small g is equal to capital G, capital M upon capital R square, right? That means R is inversely proportional to small g since R is in the denominator and G is in the numerator. That means when we have the value of R as more, G will be less. And when the value of R will be less, G will be more. So when we talk about the equator, we know that the value of R at the equator is more, right? That means the value of G will be less as compared to the poles, and the value is 9.78 meters per second square. Why meter per second square? Because it is acceleration and the unit for acceleration is meter per second square. Now we'll talk about the poles. When we talk about the poles, again the radius is less. Now since the radius is less, the value of G would be more, and the value of G is 9.832 meters per second square. But the average value of small g that we consider is nothing but 9.77 meters per second square. So this was in terms of shape. Now we'll talk in terms of altitude. Altitude means height. That means whenever height changes, whenever height from the surface of the earth or the center of the earth changes, we know that the value of G will also change. We have this formula, small g is equal to capital G, capital M upon capital R square. And we know that when the distance between their centers change, we know that G will also change, and R is inversely proportional to G. That means when altitude increases, G decreases. Why? Simply because R is inversely proportional to G. So this was in terms of altitude. Now we'll talk in terms of the depth. Now we know that the gravitational force exerted by any planet, or let's say Earth, is from the center of the Earth. That means now when we are on the surface of the Earth, the amount of mass that is responsible for the gravitational force is the entire mass. Now let's say for some reason this person doesn't like to be on the Earth and he wants to dig a hole and go inside the Earth. Now if you see the effective mass or the mass under consideration, you have to memorize this, mass under consideration. Repeat it, mass under consideration. So now the mass under consideration has decreased. Now since the mass under consideration has decreased, here you can see mass is in the numerator and G will be directly proportional to mass. Now since mass decreases, G also decreases. Now if it goes even further, that means when the depth increases, again the value of G will decrease. So whenever depth increases, the value of G will keep on decreasing. But now you see, when he reaches the center of the Earth, do we have any mass there? No, right? That means when mass becomes zero, G also becomes zero. So if there is a question in your exam, what is the value of G at the center of the Earth? The simple answer would be the value of small g at the center of the Earth is 0. Why? Simply because mass under consideration is 0. So that means here we have the three reasons: shape, altitude and depth for the variation in the value of small g.